Isotopes are actually a very simple concept. It is simply atoms of the same element that have different masses. Those are isotopes. So it's all atoms of one element. So all carbons, for example, but they have different atomic weights because they have different number of neutrons. We used the example earlier of carbon 12, carbon 13, and carbon 14. Now these are the three carbons that exist in nature. I didn't make these up for illustration. These are actually the three that exist in nature. We know that it's carbon, so we know that there are 6 protons, right? So we can list the protons. In each case, it's carbon, and carbon is defined by having 6 protons. That doesn't change. The molecular weight, or the atomic weight in this case, or the atomic mass, is 12, 13, and 14. We know that the number of protons plus the number of neutrons together sum to the atomic weight. So that means the neutrons, in the case of carbon 12, are 12 minus 6, or 6 neutrons. In the case of carbon 13, it's 13 minus 6, or 7 neutrons. And in the case of carbon 14, it is 14 minus 6, or 8 neutrons. All right, same element, you just tacked on another neutron. Doesn't change the charge in the nucleus because neutrons are uncharged. Doesn't change the number of protons. If you change the number of protons, that creates a different element. It's just like you have a little hanger-on in the form of another neutron or 2 neutrons or maybe many more depending on which element you're talking about. Here we're talking about carbon, and there are just 3 isotopes of carbon, 12, 13, and 14. You can think about isotopes maybe a little bit like a Ford F-150. If you buy a Ford F-150, you can buy different styles, right? An XLT, an XL, or an STX, but they're all still Ford F-150s. So they're at their core, they're still the same. It's sort of like you had carbon 12, carbon 13, and carbon 14. At their core, they're still carbon. They're still the same, but they're slightly different models because they have different numbers of neutrons. We know that the periodic table doesn't list the individual isotopes of each element, right? You can find those lists many places, but in the periodic table, it's simply the element. And that makes sense because isotopes are just different forms of the same element. Carbon's still carbon if it's carbon 12, 13, or 14. What we do show in the periodic table is the atomic weight. And that tells us the average mass of an atom of that element as found in nature. I'll show you an example of that with chlorine in just a sec. So one analogy might be that the average age of the students in a class may be 22, even if there are no students with that exact age. Same thing on the periodic table. The atomic weight is the average of the mass of all atoms found in nature of that element, but none of them may weigh, say in the carbon, exactly 12.011 as shown on the periodic table. Here are 2 isotopes of chlorine, chlorine 35 and chlorine 37. They're both chlorine, which is atomic number 17, so they both have 17 protons, and in the neutral atom, they have 17 electrons. What changes? The change here is in the number of neutrons, 18 for chlorine 35 and 20 for chlorine 37. So over on the right here, this is the percentage of atoms in the world, in nature. So 75.8% is chlorine 35 and 24.2% is chlorine 37. So let's see if we can calculate the mass number, the average mass shown on the periodic table. So we have for chlorine 35, we have mass of 34.9689 times 0.758, right? That's your percentage here, taking the 0.758. And chlorine 37 is going to be 36.9659 times 0.242. So if you do the math for each of these, you can do that here, and that sums to 35.45, right? So I'll let you fill in these two blanks on your own, but they sum to, I did the math earlier, they sum to 35.45. And if you look at the periodic table, you see that chlorine has an atomic mass of 35.45. All right, which of the following pairs of atoms are isotopes? So you have an atom with 7 protons and 8 neutrons, and an atom with 7 protons and 7 neutrons. Are those isotopes of one another? Absolutely, right? They each have 7 protons, so that means they are the same element, and the number of neutrons differs, 8 versus 7, meaning these are isotopes of one another. What about these two? We have nitrogen 14, so nitrogen with a molecular atomic weight of 14, and carbon with an atomic weight of 14. Are those isotopes of one another? No, they're not, right? Because they have different numbers of protons. Carbon has 6 and nitrogen has 7. All right, that's it. Thanks for watching. Any questions? Let me know.